Ladies and gentlemen, we're going to explore Chapter 7 mechanisms. And as we do these, please constantly review the similar reaction from Chapter 6. Chapter 6, there was one pi bond. Chapter 7, there's two. That makes the pi bonds a little more reactive in Chapter 7. Chemicals have been altered accordingly, the reagents. The mercury is not mercury 2 acetate like Chapter 6. Reminder, 6 was mercury with OAC twice. Little note to yourself, still Hg2 plus in Chapter 7. And this is Chapter 7 here. Reaction of alkynes. Chapter 6, your first step in the mechanism was to ionize the mercury. We don't have to ionize the mercury. I've already done it for you here. It's an ion. See it? Hg2 plus. So go ahead and do what you would have done in Chapter 6 with the already existing mercury cation. Attack it with the pi electrons of the alkyne. Here we go. Attack it. Make a special triangle. And this is a mechanism. You can use short forms for you don't want to draw this ring every time. You don't want to draw this ring anytime. This is not one where you have to circle it and say, I'm calling it R, because we got a short form for this ring, right? What is it again? Yeah, phenyl pH is attached to a C that's still got a double bond. Those are all original bonds there. The new triangle. Tell me how to draw the three sides of the triangle there. They're dotted, like partial bond number 1, partial bond number 2, partial bond number 3. Yes, there's still a partial pi. And the mercury sitting off the edge there. It's in one of the corners. It went from a +2 to a +1. And where'd the second plus end up after the reaction is over? In the center. Yes. Hearing good things from you. And what's going on here? And we have water. That triangle. Hey, every time you make a triangle, what's the step right after it? Backside attack on which carbon? It's always the same answer. More substituted carbon, which is that the one right above the water there. Only the one arrow, please. We don't have arrows to indicate partial bonds breaking. Don't invent this arrow. It doesn't exist. So we have phenyl goes to C, double C. I'm gonna draw it here so I can draw the water from underneath. And the mercury is still on top, but it's got a real bond now. The partial triangle electrons, all of them are now here in this one sigma bond. That's where they are. They shuffled over there. And you have an oxonium, and the only question when you have an oxonium is, do you neutralize it? And the answer is yes. Because we need to get an alkene attached to an alcohol, so later we can do that funny tautomerization. But right now I need the best base. What are the bases available? Well, you have water. Water's not a bad choice. And I have sulfate. Yes, which one's sulfate? SO4 2-. Yeah, the anion is actually not just hanging around for the ride. The anion is the base. Here's another way of drawing SO4 2-. It's got a little more information. Just in case some of you are going to study this and say, where the heck did that come from? So he's putting this there to remind you. It was there from the beginning. And it's grabbing the H. And I'm not upset that you didn't know that was the best base here, because you don't know the pKa of hydrogen sulfate. So you really couldn't answer the question, what is the best base here? So you made bisulfate. Yes, or hydrogen sulfate. They're the same thing. And more importantly, you made an enol that has a mercury on it. Whoa, sorry. Sorry about that. I'm going to try to not go much more to the right here. So I'm going to put this underneath. You got your double bond with your mercury. And you got your phenyl. And now it's an enol on the more substituted carbon. You're wondering what's next. It's an enol, but before you do tautomerization of the enol, you have to do something called, and it's a new name, that's why it's showing up here. Protolysis. Lurking at the top of the screen is a strong acid that, interestingly, we haven't used yet. You should be very surprised that sulfuric acid isn't being used till step number 1, 2, 3, 4. Because it's a strong acid, you're tempted to use it immediately, right? That's what strong means. Use it, it's strong. That's how strong mercury 2+ is as an electrophile. Its reactivity is much higher than sulfuric acid. This is profound, people. Sulfuric acid, you know, strong stuff, right? I'm telling you, mercury 2+ is that much stronger. It's reacted already. But now, sulfuric acid is available to do what this word says. I love the word, by the way. I love a word that says what's happening. And it's exactly a proton from sulfuric acid in black is going to cut the mercury off. Cut. Life. And what happens is, if I'm this pair of electrons here, and I have to break, which atom gets them? Carbon or mercury? It's a metal attached to a nonmetal. Always guess the nonmetal when that question's asked, because nonmetals are more electronegative. So carbon is going to take those electrons and pick up a proton. Mercury is left without a bond that it had before. Mercury is going to become 2+. And there's a furry animal at your door scratching away there. What the heck's he talking about? What's that furry animal scratching at the door? The catalyst has come back. Meow. No, you don't get bonus points for writing meow. I'm sorry. And we've got a proton in its place. Love the name protonolysis. You got a F and you got an OH. This is the tautomer. Oh, that's a funny word. A tautomer of the first product, which we can't see. If I move the pi bond and the proton here, I can get to here. You see that? Move the position of this pi bond to be a carbonyl. Move the proton from here to being on the end carbon. Makes the end carbon a CH3. That's a CH3, right? CH3? Right now it's a CH2. The only reason I drew this H is because it's new. You could have left it blank. You could have written this and you'd still get full credit. Right? You could have done that. But I wanted to show the H. So the coolest thing is the tautomerization because it's new. We're only making that product. This is a new reaction, so it's going to look a little fast and a little much the first time. Tautomerization is catalyzed by either a strong acid and its conjugate base, or a strong base and its conjugate acid. Which one do we have available in this set of chemicals? And remember, if it's here, you can use as much as you want. And I don't think a strong base is allowed in this question. You know that, right? Because a strong acid is present already. So you're going to use sulfuric acid again. I want to remind you, the first time you used it, it was a reactant. 1-to-1 stoichiometry. So if you only had a mole of sulfuric acid in there, it is now gone because a mole of this reacted with it. So what you would have to do, and you do this, is just say like, there's excess sulfuric acid. Now, some of you have been watching my videos a little ahead of time, I hope. I do have a short form for the word excess that I'm going to use extensively until the end of time. Okay, and what is my short form for excess? Excess. Good answer. She just said XS. It's the homonym version of the word, right? The letters sound like the word. I love it. So now I'm going to use sulfuric acid as a catalyst. And here is the partnership of sulfuric acid right here and its conjugate partner, which is right here. And I want you to be looking at that ketone and tell me, first thing, there's a carbonyl at the top of the page, right? That's a double bond to O. There's no H on the O. No H on the O. So what do you think the base's job is? In the catalyst, we have the base and the acid, and I forgot to draw the second H on the end. I apologize for that. And whoa. We got rid of a reaction arrow and my last edit. I don't know how. That reaction arrow was huge too. Okay. Tricky. Save just in case. What do you think the base does? Attacks the proton. Which proton? Which proton? The OH. So the base attacks the proton. And what do you think happens to the sigma bond between the O and the H? Keeping in mind, you need a carbonyl when you're done. Yes, the sigma becomes a pi. Remember all these words so we can do it in the next mechanism as well. I wanted to be very clear, the sigma becomes a pi. And the old pi breaks and picks up a proton. From where? The old pi breaks and picks up a proton from where? The strong acid. They are nice arrows. You notice how they flow away from each other? And that gives us the ketone. That last step has got a fancy name. Let's give it its due. I like that one. Oh, I don't know if my arrow is big enough now. Tautomerization. I know we've introduced it earlier. A pi moves. That's one part of it. And the other part is a proton moves. And there's your summary of tautomerization. Yeah, and that's exactly what happened, right? And the two isomers are called tautomers. So that word snuck out earlier. This is a tautomer, this one here, a tautomer of this one, in the process of going from one to the other interchangeably back and forth. Tautomerization. That's the end of our first activity. Where's the carbon? There's two carbons here, C and C, and here they are, C and C. Carbon became a carbonyl, and CH2, there's an H here still, became CH3. Second carbon there.
Where'd you get the H2O from in the beginning? 'Cause I don't see it before.
Oh, there's more water than anything. She asked, where did the water come from? And my answer to her is, there's more water in this reaction than anything. And how did I know that? Aqueous. This thing is surrounded by water, swamped by water. The predominant chemical, because it's the solvent. And it's also a reactant, right? Yes.
Are we gonna get these maps where we have to put the solvents, we have to put the reagent?
Oh, yes. Roadmaps. Yes, we've done videos on roadmaps already, haven't we?
Yeah. The same one as like the.
Yes.
I noticed that we gotta memorize the reagents, like the HOS.
Yeah, but on a mechanism, you're always given the reagent. So you're never providing me with chemicals for mechanisms, ever.
I noticed for the HG, the demercuration,
Yes.
we have to put we have to memorize that reagent.
Oh, yeah, well, that's a different type of test question. Now we're talking about roadmap type question, which you brought up, where one of these three pieces is blank. That's a whole new question. I will not mix those together, because if you screw up the reagent question, how the heck could you get the mechanism right? So we don't do that ever. Mechanism separated, tested. Now I could ask another part, which product is major and why? You know, it's a favorite, and it could be asked at any time for any reaction. And I did have the circle, and then it mysteriously disappeared. Do you remember that? Yeah, it's very weird. And if you had to explain why you circled that one, you'd have to go back to where water introduced itself, and you would say water attacks, yes, the more substituted, but no, but what you were saying was right. It's about conjugation, which is hyperconjugation. Yeah, water attacks the more substituted C, because that C spends more time with a plus charge. And you should try to sneak in the word. Why does it spend more time with a plus charge? You can use the magic word. It's got more hyperconjugation. So if asked why, if asked why, and there you go, you got a self-contained kind of thing going on there. And that sounds like the end of a video.